Alright, hey, welcome to lesson 3 for CSE 215, discrete structures. We spent the first two classes talking about sets and set theory, and all of that material is kind of foundational to what we're doing the rest of the course, but it's foundational in being sort of essential background, not so much stuff that we're going to, be working with sets directly going forward, but it's always going to kind of be part of what's making what we do work. So don't forget the stuff that we were doing last time, but we're going to switch into a new topic today, and we're going to be talking about propositional logic. And this is a pretty key subject for computer science, for some obvious reasons, some less obvious reasons. But we're going to spend about two classes talking about propositional logic, and then we're going to switch over to something else, and then we're going to come back to this and extend it with something called mathematical induction, and that's going to have a very direct tie-in to some of the things we do in our data structures course, specifically working with recursion and recursive programming. So let's start with propositional logic. And if we're going to talk about propositional logic, we need to understand, what does this word mean, propositional? So let me give you a definition of a proposition. So a proposition is a declarative statement So it's a declaration that has a truth value. So a truth value means that it's either true or false. So, for example, my name is Nick. That is a declarative statement. It is making a declaration, and it has a truth value. In this case, this is a true proposition. My name is Bob. That is also a proposition. It happens to have a truth value, which is false, because my name is not Bob, my name is Nick. 1 plus 1 equals 5. That is a declarative statement. We understand from algebra that this is a declaration which states that this side is equal to that side. And this asserts that 1 plus 1, which is 2, is equal to 5. That's not a true statement, but it is a declarative statement, and it has a truth value, in this case false. So this is also a proposition. So those things are propositions. Here's some things that are not propositions. Go away. That's an imperative. It's a command given to somebody to leave, right? But it is not a declaration with a truth value, so that's not a proposition. Who are you? That's a question. It's a statement, but it's not a declarative statement, so not a proposition, not a proposition. These things are propositions. All right? And this may have seemed obvious a few minutes ago, but this is a really important definition, because when we start working with proofs, what you're going to find is that as you write a proof, every statement you write has to be a proposition. And guaranteed, sooner or later, some of you will fall into the habit of writing proofs where the things you are stating are not declarative statements. They're not propositions. And when that happens, I will, put a note on there saying not a proposition with an arrow pointing to it. And you'll want to come back to this definition and think, okay, what is a proposition? Oh, it's got to be declarative, right? So when you write something like x squared, it's not a proposition, right? It's a indication that the value of x should be multiplied by itself. But when you write something like this, x plus 1 squared equals x squared plus 2x plus 1, that is a proposition. It's a statement that this expression is equal to that expression, and under normal numeric systems that we're familiar with, this is a true proposition. So keep that definition in mind. This idea of propositions is what we can use to talk about something called propositional calculus. Calculus just means calculation, right? It comes from the Latin word for stone or pebble, and pebbles were used for calculation, right? Something like an abacus in the dirt. And so the calculus that we study in school is, so named for being a tool of calculation. Well, propositional calculus is about some of the calculations we can do involving propositions. And one of the main things we're going to do is generate new propositions from old propositions. So if we have a proposition, we can use it to create a new proposition in very specific ways. And this notion of propositional calculus is very old. It goes back to at least 300 BC, Aristotle. So the Greeks studied this. It was most likely studied long before that as well. One name that you may be familiar with is George Boole. In the 1850s, Boolean algebra, we study this in CSE 250, is named for George Boole. And this was an attempt to take some of these ideas of propositional logic and put them on a more mathematical foundation. And this, of course, worked nicely when we started developing mechanical and electronic computing systems. Boolean algebra was a great language for developing and understanding and studying those systems. So let's look at something that's going to look a lot like Boolean algebra. Let's look at this idea of generating new propositions from old propositions. So the first operation we can talk about is negation. Now, I don't want to have to keep writing sentences like my name is Nick, or if it rains then I'm going to get wet. So we're going to work with this idea of a propositional variable. And this is just like a regular variable in algebra. So a propositional variable is a letter that represents some proposition. So for example, I can say let P be the proposition it is raining. And when you define propositions, I'm going to insist that you do it like this for this course. Don't say P equals it is raining. Don't say P colon it is raining. Don't draw a circle around this and write a P next to it. Spell it out, be explicit. Let P be the proposition, and then state the proposition. Put it in quotation marks. It's worth it. It takes a little bit of extra time, a little bit of extra writing, but I guarantee you it will save you from getting into trouble down the road. Because we've got to be really clear, number one, that we're working with propositions, and number two, what our propositions are. Okay, so let's talk about operations on propositions. So let's start with negation. So negation is this symbol that we call a hook. It's a horizontal line with a little vertical notch on the end. And if we say negation of P, this means not P. Alright, so if P is the proposition that it is raining, this means not it is raining. Well, that's not how we speak in English, right? We would say it is not raining. But the meaning of this is, it is not raining. This proposition, it is raining, is not true. The negation of this is true, right? So not it is raining means it is not raining. So this is a new proposition. This thing, the negation symbol followed by P, is a declarative statement. And in this case, the declaration is it is not raining. And so we can describe the behavior of this negation operation using a table. So we can make a table like this. Now P is a proposition. It has a truth value. It is either false or it is true. And the way negation works, if the proposition P is false, then the negation is true. And if the proposition P is true, then the negation is false. And you should recognize this again from Engineering CSE 250. This is what we call a truth table, because it's a way to sort of understand the truth of this proposition based on the truth of its input, if you like, this proposition P. All right, so we can use these same ideas to define more operations. So the next operation is conjunction. And let's just suppose P and Q are two propositions. So we can write P, and we can put this thing called a caret Q. And this is an AND operation. It means P and Q. There's disjunction. And this is written by what's called a V. It looks like a V. And that means P or Q. So we have conjunction, disjunction, and negation. And we can also write truth tables to explain how these operations perform. So if P and Q are propositions, they each have a truth value. There's 4 possibilities. They could both be false, they could both be true, or one could be true and the other false in 2 different ways. So the conjunction works like this, and the disjunction works like this. So let's do an example. So we're still going to have P be the proposition that it's raining. Let Q be the proposition today is Monday. And depending on when you're watching this, Q might be true, might be false. P might be true, it might be false. So this is a proposition, P and Q. It's the following proposition. It is raining and today is Monday. That's a declarative statement. It is raining and today is Monday. And that statement will be true in exactly the case where it is Monday and it is raining. This proposition, P or Q, is a declarative statement which says it is raining or it is Monday. And there's multiple cases where that can be true. It could be true if it's raining. It could be true if it's Monday. It could be true if it's raining and it is Monday. In fact, the only time that P or Q is not true is if both P and Q are false. So if it's a sunny Tuesday, then this proposition is false. The proposition, it is raining and it is Monday, will be false if it's a sunny Tuesday. If it's a sunny Monday, this is true. Right? What does it mean if it's a sunny Monday? Well, it means P is false, but it's Monday, Q is true. The disjunction is true. So it's just an or, right? I don't want you to think that it's more than just a simple and, an or, and a not from Boolean algebra. But I want to be clear that it is exactly the same thing when we're talking about propositions. And that's important because a lot of the stuff we did in 250 with Boolean algebra, with some of the identities and so on, will carry over to propositional logic. All right, there's one other operator which we call the exclusive OR. And this doesn't come up too often, but it's worth mentioning here. So P, X, or Q. And this is the same as disjunction, except only one of these can be true, P or Q. If they're both true, then this exclusive or is false. So it's raining, exclusive or today is Monday, means either it's raining or today is Monday, but not both. And that's just, a good old XOR operator again from Boolean algebra. All right, so those are our basic operators that we're familiar with already. Here's an operator we may not have encountered. This is called a conditional statement. And throughout all of this, we're just going to assume P and Q are propositions. So here's a new proposition, P arrow Q. So this is the proposition, if P, then Q. So it's an if-then statement. And we call P the hypothesis, and we call Q the conclusion. So if some hypothesis, then some conclusion. So let me give you some example propositions to work with. Let P be the proposition, it is raining. And let Q be the proposition, I get wet. Because I don't have an umbrella with me. So P arrow Q is the proposition, and it's literally just if followed by this proposition, if it is raining, then I get wet. This is a proposition. It's a declarative statement. It's a statement that if it is raining, then I get wet. Now that might be true, it might be false. It might be that I am indoors and so it's raining but I don't get wet. Or it might be that I'm swimming and it's sunny out but I'm getting wet anyway because I'm in the pool. So this could be true, it could be false, right? But it is a proposition. It's a declarative statement with a truth value. All right, so let's look at equivalent forms of this if-then statement, because we're doing this course in English, and English is a human language. Human languages are generally less precise than formal languages, like the language of propositional calculus. And so just like, this statement of not it is raining, that's what it actually means to put a not in front of a proposition, but we would say it is not raining, and we have to understand that means the negation of it is raining, because in English we put the not in front of the verb, right? So let's look at some other forms of this if-then statement. If it is raining, then I get wet. That's a pretty typical way to phrase this if P then Q. But sometimes we might say if P, comma, Q. If it is raining, I get wet. And the then is kind of implied. So that's equivalent to if P, then Q. P is sufficient for Q. Well, that's not something we say every day. It is raining is sufficient for I get wet. Well, that's a weird way to speak, right? It is raining is sufficient for I get wet, right? What that means is that the truth of the statement, it is raining, that's all that's required for I get wet to also be true, right? It's a kind of weird, long-winded way of saying if it is raining, then I get wet. Here's another way we could write this. Q if P. I get wet if it is raining. Well, that means exactly the same thing as if it is raining, I get wet. We could say Q follows from P. I get wet follows from it is raining. So there's lots of different ways we can phrase this, and generally it should be clear from the way problems are written what the proposition is actually saying. But just be aware that sometimes there can be an element of confusion there because English is imprecise. So we'll dig into this as it comes up. All right, so let's look at the truth table for a conditional statement. And this is going to be a little counterintuitive, perhaps. So again, we've got 4 possibilities for the values of P and Q. Okay, this says if P then Q. Well, suppose P is true and Q is also true. This conditional statement, pretty undeniably true. Because this says if P is true, then Q is true. And if we look and P is true and Q is true, then yeah, if P, then Q. That's true. And similarly, if P is true and Q is false, this conditional statement is absolutely false. Because what does this say? It says if P is true, then Q is true. Well, in this case, P is true and Q is false. So this if statement is absolutely false. These first 2 rows are a little trickier. So what it's going to turn out to be is that in these first 2 rows, the conditional statement is true. But that may be a little hard to see and to believe just from thinking about it. So let me give you some example propositions that will perhaps help with believing these first 2 rows. So I'm going to make a pair of propositions. Let P be the proposition that x is bigger than 100. And let Q be the proposition x is bigger than 1, where x is some number. Alright, so P arrow Q is the proposition if x is bigger than 100, then x is bigger than 1. And I think you'll agree this is a true proposition. If I pick some number and it's bigger than 100, it's definitely bigger than 1. Right? It's got to be at least 101, right? And that's going to be bigger than 1. So we expect if P then Q should be true. So let's look at some particular values of x. Suppose x equals 500. Well, proposition P says x is bigger than 100. Well, 500 is bigger than 100, so P is true. Q says x is bigger than 1. 500 is bigger than 1. Q is true. So we're in this case down here. P and Q are both true. And yeah, if P then Q, that's also true. Now let's pick the case x equals 0. So is 0 bigger than 100? No. So P is false. Is 0 bigger than 1? No. So Q is false. So if x is equal to 0, we are in this first row. P is false and Q is false. But that does not mean if P then Q is suddenly false. Because it's still a true statement that if X is bigger than 100, then X is bigger than 1. That is still true. So if P then Q is still true. And now if I pick a value like X equals 10, well, P is the proposition X is bigger than 100, that's false. Q is the proposition X is bigger than 1. Well, 10 is bigger than 1, so Q is true. So now we're in this case where P is false and Q is true. But again, if P then Q, that's still a true proposition. The fact that P happens to be false does not change the fact that if X is bigger than 100, then it's also bigger than 1. So this is still true. The only time that if P then Q is false is this third row. And guess what? There's no X that corresponds to this third row. Because if I found an X where P was true and Q was false, that would mean I found some number bigger than 100, but not bigger than 1. And there is no such number. Right? Which is exactly what this P implies Q means. Right? This if P then Q means if X is bigger than 100, then X is bigger than 1. Alright, that may or may not make your head spin a little. That's okay. For now, we're going to take this as the truth table for if P then Q, for this conditional statement. And as we work with it, I think it will feel less quirky. But for me, when I first encountered this, it made no sense whatsoever. But work with it, take it on faith, and come back and revisit it, and I think it will start to make sense over time. Alright, so that's the truth table for if P then Q. Continuing, more ways to make new propositions out of old propositions. So consider the proposition if P then Q. There's three other propositions we can create from this. One is called the converse. And the converse says if Q, then P. The inverse says if not P, then not Q. And something called the contrapositive combines these two. It says if not Q, then not P. Okay, so let's go back to our earlier propositions. Let P be the proposition it is raining. Let Q be the proposition I get wet. So our original proposition says if it is raining, then I get wet. The converse says if I get wet, then it is raining. The inverse says if it is not raining, then I do not get wet. And the contrapositive says if I do not get wet, then it is not raining. And I'll put the original down here. If it is raining, then I get wet. Alright, so P says it's raining, Q says I get wet. If it is raining, then I get wet. That's P implies Q. The converse, if I get wet, then it's raining. The inverse, if it's not raining, then I do not get wet. And the contrapositive, if I do not get wet, the second thing, then it is not raining, this first thing. So let's suppose that this original proposition is true. If it is raining, then I get wet. Let's suppose that's a true statement. I don't have an umbrella, I'm outside, I don't have an invisible force field. If it is raining, then I get wet. Okay, given that, is this converse also true? If I get wet, then it is raining. Well, no, maybe I just walked through a lawn sprinkler. Maybe I just jumped into a swimming pool or fell into a pond. Right? So this does not follow from that. And similarly, if it is not raining, then I do not get wet. Well, that's not true. Again, I might be standing in a lawn sprinkler. It's not raining, but I'm still getting wet. So the converse and the inverse are not the same as this original proposition. But it turns out the contrapositive is. So think about this statement. If I do not get wet, then it is not raining. That is absolutely true, assuming that this original proposition was true. Because this says, if it's raining, I get wet. So if I'm not getting wet, it cannot be raining. Why? Because we've said it's true that if it's raining, I get wet. So the contrapositive is actually the same logical value as this original proposition. So we can talk about this idea of logical equivalence. And we write logical equivalence with this triple equal sign. And it means two propositions always have the same truth value. Depending on the values of their variables. And so we can make a statement now. If P then Q is logically equivalent to if not Q then not P. So conditional is always logically equivalent to its contrapositive. And it turns out the converse, well, its contrapositive is just the negation of P implies the negation of Q. Well, that's just the inverse of our original proposition. So a proposition is equivalent to its contrapositive, and a proposition's converse is equivalent to that proposition's inverse. Lots of terminology, don't worry too much about it. Put it in your notes, jot it down somewhere where you can refer to these terms and know what they mean. And we're going to use them so much that they'll become second nature eventually. Alright, so again, more ways to create new propositions from old propositions. Alright, there's one more thing related to this. This is called a biconditional. And we can write this as P and a double-headed arrow Q. And this means, I'm going to use some parentheses here to remove some ambiguity. This means if P then Q and if Q then P. So if P then Q and if Q then P. Again, English not so precise, right? This formulation with parentheses very clear. This could be interpreted, if we didn't have the commas, as if P then Q and if Q, or something like that. So so this is more precise. But in English we could say if P then Q, also if Q then P. A simpler way of saying this is Q if and only if P. And this statement, if and only if, happens enough that we have a special abbreviation for it, which is IFF. So we could say Q if and only if P. And that means this biconditional statement. right, well, we had a truth table for P implies Q. Let's make a statement, a truth table for the biconditional P if and only if Q. So this means if P then Q, and also if Q then P. So when you're trying to write truth tables and they have multiple pieces to them, don't try to do it all in your head. Break it out step by step. So I'm going to make a column for if P then Q. And I'm just going to copy what we already had here. So if P then Q has this set of values. And now I'm going to make a second column for if Q then P. Well, if Q then P, remember it's going to be true except when the hypothesis is true and the conclusion is false. So the hypothesis is Q. If that is true and the conclusion P is false, then this conditional is false, and in all other cases it's true. So now I'm going to write a column for the following compound proposition: P implies Q and Q implies P, which is the long-handed way of writing P if and only if Q. And to do this, all I need to do is look at this column and look at this column and take the conjunction, take the and. So true and true is true, true and false is false, false and true is false, true and true is true. So there's the truth table column for P if and only if Q. And so anytime you need to figure out a truth table, you can do it by working in pieces like this. So there's going to be some practice problems for all of these ideas, all of these concepts, to get some first-hand experience with doing these kinds of things. Let's do another truth table example. So let's write a truth table for the following proposition: P or not Q implies P and Q. And we're not going to try to figure out what this means logically. We're not going to convert it to English and try to understand it intuitively. We're just going to work very mechanically. We've got two variables, P and Q. Those are propositional variables, which means they can each have a value of true or false. So we've got four combinations: false, 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 true, true, false, true, true. Boolean algebra, these are ones and zeros. So I want to write down the value of this proposition P or not Q, but I don't know the formula for P or not Q off the top of my head. I do know the formula for P or Q. So what I'm going to do is I'm going to make a column for the negation of Q, and I'm just going to look at this Q column, false, true, and write down the negation, true, false, true, false. And now I can make a column for P or not Q. This is a disjunction, it's an or of this first column and this third column. So false or true is true, false or false is false, true or true is true, true or false is true. So now I've got the column for P or not Q without having to do a whole lot of computation in my head. I'm writing down each step and I'm just using a simple Boolean operation. Okay, P and Q, that's the conjunction. That's just the and of these two columns. And if I go back to my truth table, I'll find this is only true when P and Q are both true. That's what it means to say P and Q. So now I can write down the truth value for this compound expression, P or not Q implies P and Q. And to do this, all I need to know is the truth table for if something then something. So here's a trick that you can use if we look at this conditional statement, and this is true, true, false, true, and I'll ask you not to get hung up on why these are the values they are. Let's suppose that you believed this earlier argument, and this is our truth table. Well, if I wanted to write the truth table for if A then B, right, I can do that from this truth table, even though this truth table is P, Q, and I've got A and B. It's going to be exactly the same truth table. So if I write down A, B, and if A then B, the fact that I happen to be calling these A and B instead of P and Q does not change anything. And so what may be useful, and we'll come back to this later in another context, what may be useful is to think of this as the following funny looking truth table. My first variable is box, my second variable is triangle, my third variable is circle. So false, 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 true, true, false, true, 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 false, true. And I can put anything I want in here and anything I want in here, and this will be the truth table for if box then triangle. So if this is P and Q, this is the truth table for if P then Q. If this is A and B, then this is the truth table for if A then B. But if this is not P and this is not Q, then this will be the truth table for if not P then not Q. It's the same truth table. Alright, why am I doing that? Because we are trying to come up with a truth table for if this proposition, then that proposition. And it's exactly the same truth table. This is the hypothesis, this is the conclusion. And this hypothesis is in this column, the conclusion is in that column. So what do we know about this truth table? The if then is always true except when the hypothesis is true and the conclusion is false. So let's look at this column and this column, hypothesis, conclusion. If the hypothesis is true and the conclusion is false, this is false. If the hypothesis is true and the conclusion is false, this is false. Any other condition, this is true. So there's the truth table for this compound proposition. That's all there is to it. It's a very sort of mechanical procedure. Like I say, we don't need to translate this into English and parse it and understand what it means. We can just proceed step by step. The main trick here is this idea that if we have a truth table for something like this, or conjunction or disjunction or anything else, right, we don't need a literal P and a literal Q over here. This could be any proposition, that could be any proposition. And if the hypothesis is true and the conclusion is false, then the if then is false. In the other case, the if then is true. Okay, you got some practice problems on this. We'll be doing this throughout this unit, so we'll get some more practice with this also. Last thing with these if then statements, last thing with these truth tables is this idea of propositional equivalence. And remember, we said we use these three horizontal bars, this big equal sign, to mean two things are logically the same in all cases. So, for example, if I look at the truth values of this compound proposition, they're false, true, false, true. If I look at the value of Q, it's false, true, false, true. In all cases, regardless of the value of Q and regardless of the value of P, this proposition always has the same truth value as this proposition. So we would say that this is logically equivalent to that. In other words, we could say P or Q, P or not Q, implies P and Q. Let me put some parentheses around this to say this is one proposition. This is logically equivalent to just the proposition Q. And we demonstrate that by making a truth table for this, making a truth table for that, and showing that in all situations they have exactly the same truth value. They're either both true or they're both false. So saying A is logically equivalent to B is also the same thing as saying A if and only if B. They're both true or they're both false. Alright, and we have a few particular propositions that we always kind of keep around in our bag of tricks. There's a proposition called T, and T is the proposition true. It's just a proposition that's always true. And false, F, is the proposition false. It's a proposition that is never true. So is this a declarative statement? Again, English is imprecise, but you know, I can say, you know, true, and that's a declaration, right? That something is true. So T means true, F means false. And we can use this, for example, if we look at disjunction. This says P or not P. Well, if we make a truth table, P is either false or true. Not P will correspondingly be true or false. P or not P, well, false or true is true. True or false is true. So this proposition is always true. In other words, regardless of the value of P, it is always got the same truth value as T. And so we could say this is logically equivalent to true. And similarly, the conjunction of P with not P, well, false and true is false, true and false is false. So this is logically equivalent to false. It's always got the same truth value as false, regardless of the value of P. So, so this is called a tautology. Right, something that is always true. This, which is always false, this is called a contradiction. So a tautology is always true. A contradiction is always false. Anything else is called a contingency. For example, A or B. Well, that's not always true and it's not always false. It depends on the values of A and B, or it's contingent on the values of A or B. So some propositions will be logically equivalent to true, tautologies. Some will be equivalent to false, contradictions. Most propositions will be sometimes true, sometimes false. Those are called contingencies. Alright, this ties into the last topic for this lecture, which is talking about identities. So let me write some logical equivalences here that will always be true. These equivalences are always true. So we're just going to let P be a proposition. So for example, P and true is always logically equivalent to P. So if P is a proposition, it is raining. It is raining and true. The truth value of that conjunction is the same as the truth value of just it is raining. P disjunction with false is also always logically equivalent to P. And this is an identity called just identity. All right, P and false is always logically equivalent to false. P or true is logically equivalent to true. This is called domination, because the second term determines the truth value of the entire proposition. So it is raining and false, that conjunction is false, because the only way a conjunction is true is if both propositions are true and false is not true. It's false. A disjunction is true if either proposition is true, and true is always true, so this disjunction is true. Alright, P or P is logically equivalent to P and P, which is logically equivalent to P. That's called idempotent. So it's raining or it's raining has the same truth value as simply it's raining. The negation of P is logically equivalent to P. That's called double negation. And we've got all the usual P or Q is logically equivalent to Q or P. P and Q is logically equivalent to Q and P. That's commutivity. P or Q or R is logically equivalent to P or Q, ORed with R. And the same for ANDs, that's associativity. And these may be looking familiar to you, perhaps from Engineering CSE 250. This one will sort of nail that down. The negation of P and Q is logically equivalent to the negation of P disjunction with negation of Q. And the negation of P or Q is logically equivalent to negation P conjunction with negation Q. And these are both versions of De Morgan's theorem. So there are all of these identities, and there's other identities as well, and they all correspond to things that we find in Boolean algebra. So so you'll want to write these down on your note sheet, put them somewhere where you can refer to them going forward. And I'll also have on Canvas a set of these identities that you can download and print or just refer to online. So those identities can help us with showing certain things about, say, logical equivalence. So let's do something that's going to look a little like a proof. So as an example, let's show that the negation of P or not P and Q is logically equivalent to negation of P ANDed with negation of Q. Now when you're asked to show that two things are equivalent, you can use identities to transform this until it looks exactly like that. Or you can use identities to take this and transform it until it looks exactly like that. But what you're not allowed to do is apply identities to both sides and change them each into something else that are equivalent to each other. That is not a valid way to show equivalence. And I'll give you a really silly example. Prove 1 equals 2. Well, if I start off with 1 equals 2 and I multiply both sides by 0, I get 0 equals 0, which I know is true. Does that prove that 1 equals 2? Of course not. Now, if I start with 1 and I can do some things to that and eventually turn it into 2, then I've got a valid proof. Or if I start with 2 and I do some things to eventually turn it into 1, that's a valid way to show these are equal. But doing something to both sides and ending up with something equal does not prove that you started off with two things that were equal. And that's a silly way of seeing where, that would be a fallacy. Alright, so let's start with the left side and let's use our identities to show that this is logically equivalent to that. And the first thing I'm going to do is I'm going to use De Morgan's theorem. And let me rewrite De Morgan's theorem in a slightly different form. I'm going to say negation of box or triangle is logically equivalent to negation box ANDed with negation triangle. Okay, why the funny shapes? I can put anything in here as long as it also goes in there. I can put anything in my triangle as long as it also goes there. So I can put a P in here and I put a Q in there, and I've just got plain old De Morgan's. Not P or Q is not P and not Q. But I can do other things also. I could, if I prefer, and if I can write very small, I could do the following. Because I'm trying to transform this expression up here. Well, this is not P ORed with this other expression. So I'm going to put P inside my box. And in my triangle, I'm going to put not P and Q. Like that. And De Morgan's still applies. So let me write this down. I'm going to start off with not P or not P and Q. So not P or not P and Q is logically equivalent to not P ANDed with the negation of not P and Q. And my reason for that? De Morgan's theorem. Alright, I'm going to use De Morgan's theorem again. I'm going to use it on this piece of my expression. So I'm going to say not P or not P and Q is logically equivalent to negation of P ANDed with, and I'm going to replace this with some other expression. So let me write De Morgan's theorem again. It says not, this is the other form of De Morgan's theorem, not box and triangle is equivalent to not box ORed with not triangle. Okay, I'm trying to manipulate this thing which says not P and Q. So my box is going to be not P, and my triangle is going to be Q. Now you don't need to use the boxes and triangles once you get what's going on here. This is just sort of a way to to take De Morgan's theorem and see how to apply it to something that doesn't look like, not P and Q, for example. So De Morgan's theorem tells me that this thing, not P and Q, is equivalent to this thing, not P or not Q. So I'm going to replace that over here. This is not P or not Q. And that's De Morgan's theorem. All right, I'm going to keep going. Not P or not P and Q is equivalent to, I'm going to leave my not P here, and we have a rule called double negation, right? Double negation said not P is equivalent to P. So this not P, I'm going to replace that with P or not Q, and that's double negation. Alright, and we're just going to keep going like this. Alright, well, here I have an and here I have an or. So let me give you another identity. So P and Q or R is logically equivalent to P and Q ORed with P and R. This is called distribution. Alright, now I could do this with boxes, triangles, and circles, but let's do this one a little bit in our head. So let me rewrite my left side. Not P or not P and Q is logically equivalent to, okay, so I have something anded with something or something. And my distribution identity says this statement here is logically equivalent to my first something, which is not P, anded with my second something, which is P, ORed with my first something, which is not P, anded with my third something, which is not Q. That's distribution. Okay, if that didn't make sense, go back to the triangle, squares, add a circle, and plug in this for the first thing, this for the second, this for the third. Alright, so there's my distribution. Let's keep going. Not P or not P and Q is logically equivalent to, well, not P and P. Alright, well, there's another identity which says P and not P is logically equivalent to false, and this is called negation. So this not P and P, I can replace that with false or not P and not Q, and my reason there was negation. And now not P or not P and Q is logically equivalent to, well, I have another identity here. I have false or something, and I had an identity which said P or false is equivalent to P. Right, that was something we call the identity property. So a disjunction with false just gives me my original proposition. So this thing ORed with false is logically equivalent to not P and not Q, and that's identity. And so by just manipulating this left side, I have shown that this proposition is equivalent to not P and not Q, which is the thing I was trying to show. So that's a valid way to show that two propositions are equivalent to each other. But again, you can work with one side or the other. You're not allowed to change both sides. right? If you're going to do that, you have to do it in a very particular way that is reversible. And one final detail, you'll notice that this identity property actually was not F or P. It was P or F is equivalent to P. But here I had F or this thing. I kind of skipped a step. I really should have added a step claiming that this was equivalent to this thing ORed with F. In other words, used commutivity to switch those around, and then my identity property, as I stated it, would have applied, because this applies to P or F. Or if I like, I could just simply add to my identity and say, hey, this is also the identity. F or P is logically equivalent to P. And if I'd written my identity statement in that form, then that would clearly apply to this. F or this thing is just equivalent to this thing. So we don't want to skip steps in general, but if it's just a matter of, you want to use something like this, P or true is true, and you've actually got true or some proposition, you can, take your statement as being T or P as opposed to P or T. You can do that level of shortcutting. All right, so that's an example of showing logical equivalence using these identities. So as I said, these identities will be available on Canvas for you to download, put them on your note sheets for sure. And as you're working on the homework problems, don't be going to the web to look these things up. Look at your note sheets, because you want your note sheets to be your reference for working on these problems, so that when you get to the exams, you've already got your pages of notes ready to go, and you can work from those, and you'll be familiar with them, and so on and so forth. So, all right, so that's the first piece of propositional logic. Next lecture, we'll go ahead. We'll start talking about predicates, quantifiers, and get into rules of inference and fallacies, which will take us into our first real discussion of proofs.